in this video, this is going to be the limit comparison test. So it kind of has the same feel as the comparison test in the sense that you're going to pick something that you're going to compare it to. It's just what do we do with it is a little bit different. So we let a sub n, b sub n both be greater than or equal to 0 for all n greater than or equal to 1. And then we have three cases here. If the limit as n goes to infinity of the ratio of the two sequences equals L and L does not equal 0, then then the summation of n equals 1 to infinity of the sequence and b sub n both converge or both diverge. So in other words, what the first one is saying here is if you pick a known convergent series and you go ahead and you take the ratio of these two series and you look at the limit of that, either both of them converge or both of them diverge. So if you pick a known convergent, they both converge. If you pick a known divergent, they both diverge. Okay? 2 says almost the same thing, except if the ratio equals 0 and b sub n converges, then a sub n converges. And finally, 3, if it equals infinity and b sub n diverges, then a sub n diverges. Now, we do got to be a little bit careful here because if the ratio of the two sequences go to 0 and b sub n diverges, so the thing that you chose diverges, the limit comparison test gives no information. All right. Also, if the ratio, when you take their limit, if it goes to infinity and the series of b sub n converges, the limit comparison test, I'm going to just put LCT, provides no information either. You have to meet these specific conditions. All right? You got to meet those conditions. So let's look at one that I think we would be familiar with. So here's an example, and it's going to look similar to what we had previously, but it's not. So initially you may be thinking, oh, well, I'll just use the comparison test and I'll compare it to a p-series of 1 over n to the second. But the problem is, you probably want to compare this with this right here. But you can't. Number one, you don't really meet the conditions necessary, right? I mean, they have to be increasing and all that stuff. But even your indices kind of aren't the same. So comparison test is not going to work here. All right. Instead, let's try to use the limit comparison test. Now, we're still going to use this. It's just we're going to use it in a different way. We're going to start it at 2. And we're going to take the ratio of these two things. All right? So, we're going to find a limit as n goes to infinity of a sub n minus b sub n. This is a sub n. Here's our b sub n. So, let me give myself a little bit of space here. I like that. So here's what we got. We got the limit as n goes to infinity of 1 over n squared minus 1, all divided by 1 over n squared. Oops. All right. Now, when you go ahead and divide, you end up with this. N squared over n squared minus 1. And when you look at this, notice that the degree of the numerator and denominator are the same. And as the limit of n goes to infinity, this is just going to equal 1. That's it. So you can conclude that since the limit as n goes to infinity of a sub n over b sub n equals 1, and 1 over n squared is a known convergent series both a sub n and b sub n converge by the limit comparison test. And that's it. So for this example, we had to switch our approach up a little bit because we didn't meet the condition for a comparison test. So just go ahead and take the limit comparison test. All right, so let's look at some examples doing this, okay? All right, here's another example. Does the series from 1 to infinity of 1 over the square root of n plus 1 converge or diverge? All right. So we're going to do the limit comparison test here, and we're just going to compare it to something that we know. We know one over the square root of n is a known divergent series. And that's because 1/2 is less than 1, so it fails that p-test thing. All right? So let's go ahead, let's see what happens when we try the limit comparison test. So we're going to get the limit as n goes infinity of 1 over the square root of n plus 1 all over 1 over the square root of n, which gives us the limit as n goes to infinity of the square root of n over the square root of n plus 1. When you go ahead and you substitute in the limit, you get 1. So by the limit comparison test, since our series from 1 to infinity of 1 over the square root of n diverges, then our series 1 over the square root of n plus 1 also diverges. All right? We could do one more here. For our next example, we're going to start with from n equals 1 going to infinity of 2 to the n plus 1 over 3 to the n. Does this converge or diverge? So let's compare it. With this series. Okay? Now the question becomes, does this converge or diverge? So hopefully when you look at this, you're thinking about it as 2 to the n over 3 to the n, where 3 to the n is going to get bigger much faster than 2 to the n. So we know this converges. All right. So let's take the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n, all divided by 2 to the n over 3 to the n. That's going to give us the limit as n goes to infinity of 2 to the n plus 1. And I'll write it like this first. Over 3 to the n times 3 to the n over 2 to the n. I was going to just group everything all at once, but I figured I'd just write it like this. The 3 to the n's reduce. So we get the limit as n goes to infinity of 2 to the n plus 1 all over 2 to the n, which is the limit as n goes to infinity of 1 plus 1 over 2 to the n, which, when you go ahead and you take the limit, you end up with 1. Therefore, our comparison limit converges. We conclude that our series, let me write that nicer, 2 to the n plus 1 over 3 to the n converges as well. All right, so I hope that helps, and I'll see you in the next video.